The first topic in electricity is current. So we need to look at some of the key ideas in current. And it's absolutely essential that you understand current because all the other ideas within electricity build on a fundamental understanding of what this is. So we'll look at the idea of a flow of charged particles, the formula I equals Q over T, which you hopefully have seen previously at GCSE. We need to know what the Coulomb is, a definition of that. There's something called Kirchhoff's first law, which you may have come across before. And we're going to introduce series and parallel circuits and just talk a little bit about the differences and how current varies. So we're trying to think about applications of each of these topics, and obviously current is hugely important in the modern world. One particular scenario, which I think is very interesting, is the idea not just of a national grid, but of an international grid. So sometimes referred to as a supergrid. As far as I'm aware, these are just proposed. These don't actually exist yet, but they bring into context lots of ideas of electricity in terms of obviously current, but resistance and resistivity, maybe superconducting materials. And the idea is that you can generate lots of electricity in a place which has a lot of solar energy, or a lot of geothermal, or a lot of hydroelectric, and you can transfer this freely between countries. So really exciting, really interesting scenario which may come to pass at some point in the future. So a really key idea in electricity is the idea of delocalized electrons, which you may well have come across before, also known as free electrons. The idea is that all metals have these electrons, these charged particles, which are able to move around freely. And in a piece of wire, which is not in a circuit, then they will have energy. They'll move around with random motion, shown like this. So moving around, some fast, some slow, in all directions, and that doesn't have a net effect. However, if we have a voltage applied, then the negatively charged electrons will be attracted to the positive terminal and repelled from the negative terminal, and we end up with a flow of current. So this idea of charged particles flowing from the negative to the positive and transferring energy, as we'll see in a moment, is a key idea. And this is called the drift velocity. We'll look at this later on in this series of videos. And the random motion we mentioned previously is actually superimposed on top of this drift velocity. So if I have a circuit and I've got a battery and a wire and a bulb, for example, if I close a switch, then I'm going to get electrons moving around, as we've just described, away from the negative towards the positive, and they will transfer energy. So two really key ideas here. The current, the charged particles, the electrons rather, are not used up. So the current in a series circuit will be the same at any particular point around the circuit. Energy, however, is transferred, so that might be used up. It's transferred from chemical into other forms of energy. Okay, so let's consider how we carry out calculations, how we model this mathematically. I equals Q over T. Hopefully you've seen this before. Current is equal to charge divided by time. So current is measured in amps, charge is measured in coulombs, time is measured in seconds. Really important to make the distinction between the letter for the quantity, which is I, and the letter for the unit, which is A. Similarly for charge, Q is the symbol to represent the charge, but it's measured in coulombs, capital C. And we can define current as the rate of flow of charge per unit time. So this is another way of saying charge per second, Q over T. And we can define the Coulomb. So if I have 1 amp flowing for 1 second, then the amount of charge passing is 1 Coulomb. And the charge on 1 electron is this tiny value here, known as the elementary charge, 1.6 times 10 to the minus 19 coulombs. So 1 Coulomb represents an enormous number of electrons, and we can work out the number by finding the reciprocal of this value here. So 1 divided by 1.6 10 to the minus 19 gives us this really big number, 6.3 10 to the minus 19. Right, so a few worked examples. This is a little bit more GCSE level. If I'm told that I have 180 coulombs passing a point in 2 minutes, I can calculate the current, which is the rate of flow of charge. And all we need to do here is simply divide Q by T. So 180 divided by 2 times 60. Always check the units. So minutes multiplied by 60 gives us seconds. And we'd find that the current is 1.5 amps. So I is equal to 1.5A. We can rearrange the formula to make Q the subject. So we multiply both sides by T to give Q equals I times T. We do need to know these prefixes. So mu is micro, which is 10 to the minus 6. Little m is milli, which is 10 to the minus 3. Once again, I just multiply them together and I get the answer 10 to the minus 8 coulombs. If we wanted to find the number of electrons associated with question 2, all I need to do is divide the total charge by the charge on one electron. So we have 1.8 10 to the minus 8 divided by our value elementary charge, and we get 6.25 10 to the 10. Now there's not a formula in the formula booklet which is provided. However, if we look at the units, C divided by C, that's going to cancel, and we should end up with no units, but usually a very large number of electrons. A simpler way to think about this is if we make the numbers a lot easier. If you imagine that every electron has got a charge of 20 coulombs, and I ask the question, how many would you need to get a total charge of 100? You can probably see that quite intuitively, that we need 5 lots of 20 to get 100. So what we're doing mathematically here is to find the number of charge carriers, in my made up example, is divide the total charge by the charge on each electron, each charge carrier. 100 divided by 20 is equal to 5, which is exactly what we've done here with the realistic numbers. So this is an exam tip here. The units are really, really useful. They're going to help you work out relationships and to check your answers. So always think about the units, and certainly always include the units in your written answers. Kirchhoff's first law, you might have seen this at GCSE. You do need to know this. The sum of the currents flowing into any point in a circuit is equal to the sum of the currents flowing out of that point. This is based on the idea of conservation of charge, which means that under normal circumstances, electrons don't just appear or disappear. So they're going to stay as a constant number of electrons. So if I look at this junction here, I've got 3 wires. I1 is the current going into the junction. I2 and I3 are coming out of the junction. And hopefully you can see algebraically that I1 will be equal to I2 plus I3. So that's all we mean by Kirchhoff's first law, is the total current in is equal to the total current out. If I look at a numerical example, I've got a more complicated junction here with 4 wires, and I can see that I've got 3 amps going in here, 7 amps coming out, and 2.5 amps coming out over here. So my total out of this junction is 9.5. So the total into the junction must be 9.5. So this unmarked one here must be 6.5 into the junction. Then we have a total of 9.5 in and 9.5 out, which is Kirchhoff's first law. Right, we're going to consider series and parallel circuits. Again, hopefully you've seen these before. A series is a single loop. A parallel is 2 or more loops. And we measure the current using an ammeter. There's lots of different types of ammeters. The ammeter must be connected in series. So if you look at the series circuit here, I've got an ammeter here, A1, A2 and A3. And if I was to measure the current at each of these points, it would be exactly the same. So that's really, really key point. The current in a series circuit is the same all the way around. If I did the same with a parallel circuit, so I've got 4 ammeters now, A1, A2, A3 and A4, what I would find is the current splits at the junction and then reforms at the other junction over here. So we should find that the total current in and the total current out are still the same, so A1 is equal to A4. But because it's split here, then A2 plus A3 would be equal to A1. So both of these are illustrations of Kirchhoff's first law, as we saw in the previous slide. We could consider the question here, which is what would happen to the current in a circuit if the number of resistors is increased. So first of all, in series. So if I added another resistor, let's say another 10 ohm resistor into this circuit, then it's more difficult for the current to flow. There will be more collisions, and we'll talk about resistance and collisions later on in this series. but the greater the resistance, the smaller the current. If I did the same in a parallel circuit, if I added another loop down here, so let's say I put a 10 ohm resistor to make a separate loop down here, then as we'll see later on in the series, the total resistance actually goes down if you increase the number of resistors connected in parallel. So if the total resistance has gone down, that means it's easier for current to flow, so the total current will increase. What you need to do now is have a read through these 4 questions and then pause the video and try your best to answer them. So question 1 is some definitions. Question 2 is a few questions using I equals Q over T. Question 3 is thinking about Kirchhoff's first law. Question 4, a little bit more difficult. That's asking you to calculate the number of electrons given the information provided. So pause the video, give yourself 10 or 15 minutes to work through these questions, and then I'll go through the answers. Just play the video again, and I'll go through the worked solutions for each of these questions. Right, the definitions, you do need to know these, so top exam tip, write these down, keep a list of these. You do need to know these for the A-level exam. So we define current as the rate of flow, or just the flow of charged particles per unit time. We define 1 coulomb as the amount of charge flowing past a point in 1 second if the current is 1 amp. And Kirchhoff's first law, as we said, is the sum of the currents into a point is equal to the total of the currents flowing out of the point. Right, question 2. Hopefully these should be straightforward. Let's have a look at the first one. So I equals Q over T, we've got 25 milli, which is 10 to the minus 3, divided by 0.5 is going to give you 0.05. And I'll give you a really important exam tip here. Always show you're working out. So write the formula, substitute the values using standard form, write the answer with the units. If you get the wrong answer, you can still get several marks for a wrong answer if you show you're working out. For 2b, we've got Q equals I times T. So we've got 3.2 micro, which is 10 to the minus 6, multiplied by 6 milli, 10 to the minus 3, and you should get 1.9, 10 to the minus 8 coulombs. Once again, make the distinction between Q, which is a symbol for charge, and C, which is the unit of charge, coulombs. The final variation on this formula will be to make T the subject. T is equal to Q over I. Substitute the values, 2.5 milli divided by 7.2 micro, and you should get 347 seconds. So once again, write your answers where required using standard form. Always write the units. And in terms of the level of detail, so 2, 3, or 4 significant figures would be acceptable for the exam. Right, so we've got Kirchhoff's first law, we've got a parallel circuit. We can see here we've got 8 amps. So this is going to split. 3 amps goes along the top loop. So we must have 5 amps along the bottom loop. 5 plus 3 gives us 8. And A1 and A2 are both part of the same series section of the bottom loop. So A1 is equal to A2, those are both 5 amps. And then over here, the current will recombine, and 5 plus 3 will give us 8 amps. And final question, Q equals I times T. We can work out the total charge. Don't forget, we need to change minutes into seconds to get 225. And then if we want to work out the number of electrons, as we said previously, the total charge divided by the charge on 1 electron should give you 1.41 times 10 to the 21. So we've got no units here, and that's the end of the first lesson.